Okay, so this is Unit 5 Mastery Project for Ray Physics. Alright, this is FRQ number 4, so we have pulley with a block, and pulley with a rope. So then they're held at rest. The uniform density of omega is wrapped around pulley 2, is identical to pulley 1. Section a rope with the same mass, M2. And then both pulleys have rotational inertia of I is equal to 1/2 m1r squared. And both pulleys are released from rest. So then, at all times the pulleys are released, the angular acceleration of the blocks are non-zero. Consequently, the tension at any point is approximately equal to the weight below that. Okay, so based off that, in part A, after the pulleys are released and they start rotating, indicate which of the following claims is correct regarding the instantaneous angular speeds of the pulleys are short a non-zero delta t after they're released. So here we have that pulley 2 is greater than the angular speed of pulley 1 because, based off this here, the tension at any point in the string is approximately equal to the weight below that. So as pulley 2 is being unraveled, the mass of the rope is increasing because of gravity acting on that. Whilst the pulley 1 has most of its mass already in figure 2. So as pulley 2 is being unraveled, there's going to be more torque, longer duration of torque, and because of that, its angular acceleration would increase, and as a result, its angular speed would increase. So here, this is put as torque net is equal to inertia dw dt. Right now it has same torque net right now. So because the greater torque is going to result in greater angular speed. For part B, as a group of students finds that the angular speed of a function of t can be written as this function, where c is a positive constant, and derive an angular acceleration for pulley 2. Express your answer in terms of physical constants. So they found out that this equation is equal to the angular speed. So mass 2 r c c is a constant minus negative ct. And the definition of the linear acceleration is change in linear angular velocity and change in time. So it's pretty much the derivative of this function. So angular acceleration speed with respect to time, this would be at the front still because it's a constant, r times c, and now derivative of ect is just c e to the ct, and then derivative of negative, or e to the negative ct is just positive. Oh no, sorry, negative c. So you get positive now, and cancel or bring out the c, so that's c squared times ect plus ect Yeah, which is just 2 ECT. So we would get, wait. So you get C squared times 2 ECT. Rest of the 2 times. And then those 2's would cancel out, so we'd get mass 2 by radius C squared ECT. Oh my gosh, this is negative. So in reality, you can't add that. I can't add those together. This would just be negative e to the CT. And that would be the function of angular acceleration. And now, part 2. Using the initial acceleration of the system, derive an expression for the constant c, and then write as physical constants. Okay? So we're using the initial acceleration. And the initial acceleration is given by the hanging rope weight from pulley 2. So it would be the net torque divided by the inertia. Torque that's, or the force that's providing that torque, is gravity. So we have m2g of r divided by inertia, which was 1/2 of m1r squared. Simplify a little bit, and this would be 2. And then now we set this equal to our equation. M1 of r is equal to mass 2 over 2 times r c squared ECT plus E negative CT. And now we solve for C. Okay, so masses here would cancel. The radius would cancel. So times 4, times 2, so you have divided by omega. Times omega divided by m1 is equal to c squared ECT plus E negative CT. Missing something? Oh, at time is equal to 0. Oh, whoops. So, oh my gosh. Is plugging into 0. E to the 0 is just 1. Same thing with e to the negative CT. So that'd just be c is equal to oh my goodness. So this becomes 1 plus 1. That's just 2. So this will be 2 and 1 is equal to c squared. And c is equal to the square root of 2 over m1. And then we can plug this into our angular acceleration. This is just 2 over m1. Squares cancel out. Times e to the square root of 2 m1 times t. Plus e to the negative 2, 1 is t. And that would be our angular acceleration function. Now for part C, a third pulley with twice the mass of the first, and the same linear density, with twice the mass of the rope. The pulley is returned to the same configuration, and pulleys 2 and 3 are released. After a long time, before the ropes are completely unwrapped, the pulleys indicate whenever the angular acceleration is greater than pulley 2 or greater than pulley 3, using the equation you derived. This is 2. Twice the mass, pulley 3. Twice the size of M1. Believe that pulley 2 would have greater angular acceleration, because for pulley 3, M2, which is the rope, is now twice, M1 is now also twice. If you look at this equation, 2 since M1 is the denominator in our angular acceleration function, it would result in a much lower angular acceleration than that of pulley 3.